We've been searching for a law that does the same kind of work as Gauss's law, and that law is Ampere's law. Ampere's law tells us how currents make magnetic fields, and can be used to find those magnetic fields directly. The way it works is incredibly similar to how Gauss's law works, so I'm going to proceed by making a step-by-step analogy to Gauss's law. Gauss's law says that if you integrate the electric field over some closed area, you get a result that's proportional to the amount of charge enclosed. Ampere's law says that if you integrate the magnetic field along some closed loop, you get a result that's proportional to the amount of current that flows through the loop. The geometry is a bit different. We do a line integral of B instead of a surface integral, but it's the same basic idea. Draw some kind of closed loop, look at how much current flows through the shape bounded by that loop, and that tells you about the B field on the boundary of that loop. And in either case, the value of the integral on the left-hand side doesn't depend on what kind of shape you choose. All that matters is how much charge or current you enclose. But if the symmetry of the situation is just right, you might be able to pull out that E or B and solve for it explicitly. You can expect that to work with Gauss's law if you have a charge distribution with spherical, cylindrical, or planar symmetry. And you can expect it to work with Ampere's law if you have a current distribution with cylindrical symmetry. Let's see how this works out in practice. Every step in the procedure for solving for B fields with Ampere's law has a corresponding step in the Gauss's law procedure. So I'll do two simple examples side by side. Take a point charge for Gauss's law and a long straight wire for Ampere's law. We know that point charges are spherically symmetric and make field lines that point radially outward. Similarly, straight wires are cylindrically symmetric, and we know they make field lines that point in concentric circles. To find the E field at some point, we draw a Gaussian surface that includes that point, and we center it on the point charge. To find the B field at some point, we draw an Amperian loop that includes that point, and make the loop coaxial with the wire. Now, since the E field lines are radial, we know they'll be parallel to the area vector at any point on that Gaussian surface. And so E dot dA gives E times dA. Also, the spherical symmetry of the situation requires that the E field have the same magnitude everywhere on the sphere, so we can pull E out of the integral. And the integral of dA is just A, which is the area of the Gaussian surface. Similarly, we know that the B field lines from a wire point in loops, meaning they'll be parallel to the dl vector at every point on the Amperian loop. So B dot dl is B times dl. And every point on the Amperian loop is the same distance from the wire, so the B field must be of the same magnitude all along the Amperian loop, and we can pull it outside the integral. And the integral of dl is just L, the perimeter of the Amperian loop. The right-hand side of each law is straightforward. We enclose some amount of charge Q and some amount of current I, letting us solve directly for E and B. And there we have it. If you know how to solve Gauss's law problems, and you view Ampere's law in analogy to Gauss's law, you can double dip quite a bit knowledge-wise. Oh, and FYI, Ampere's law is part of one of the Maxwell equations, and by itself it's totally accurate in magnetostatics, where currents are steady. Eventually we'll talk about how to generalize it to dynamics too.